Okay, so, right, we had some dimensions that we were measuring, right, some characteristic dimensions. So basically what would be like these. Something like that, right? We had viscosity of fluids and even the densities of them. So those are fluid properties. And then we even had some velocity, right? Some speed index that we were doing, right? So then if you look here, right, this was always this bottom axis speed. Sort of a speed thing. Okay, so it's not too hard to imagine that you see these parameters and you look at like why those things are happening so differently. Because remember, when you dropped it in highly viscous fluids, the opposite happened as opposed to when it was air. When it's air, this thing experiences far less drag. So it's not out of the question that you could imagine that you get to a situation where you go, well, here's a good parameter on the bottom axis, a Reynolds number, right? And then you could have these two characteristically different sections of happening, where here is a laminar situation and here is a turbulent situation. Right? You can kind of see where this is headed, right? What is a Moody chart? When we had a Moody chart, right, we were over here, we're looking for friction factors. This was Reynolds. You had this straight line part, which was laminar. You had this transitionary part, which is just God all whatever. And then you have this turbulent part. So, right, is where we're headed for external flows. But the idea being, just from the experiments themselves, you could figure out that when I had a low Reynolds number with a combination of all these things, there was this law that came about that it was speed So for low Reynolds in experiments, drag was proportional to the speed times the viscosity times the size. And then in those other situations, so think of this as the glycerin experiments, and then think of this as those air experiments. This law you could derive based on looking at parameters is that the drag is proportional to speed squared times density times size squared. So that's just in words. These are two fundamentally different laws we get based on drag forces and what their proportionalities are. For the glycerin tanks, when we drop the little small things, that's characterized by a low Reynolds number. You can see that the drag force is proportional to this combination of things multiplied. When I did the air things, you could look at the Reynolds number being at high situation. So right here, you get this process of the drag being proportional to the speed squared, density, size. Already, this makes intuitive sense because what this is saying when I'm at low Reynolds number means viscous forces. So the drag force is proportional to that viscosity pops in there. High Reynolds number is, you could think of it, right, that's turbulent, or the air thing. It's not where it behaves like inviscid fluids, so it behaves as if drag has the inertial force that matters more than the viscous force. So this works, this pans out. So I just want to now go over what this little, right, what you do when you come up with these laws, right, this idea of proportionality with that little twiddly sign. So the little tilde sign, you can think of it as A being proportional to B is a statement that A is equal to some constant times B. So, and they're all of the same order. So this means that A is proportional this is an equality where C is the proportionality constant, we call it. So, and then you can have relationships different like this, but this just cues you into that terms of proportionality. Is what you really end up doing is looking for slopes of lines. And that's what you do in these experiments when you're looking for these proportionalities of drag forces. Okay? So we have drag force there, and the idea is, I should back this up. Hold all the other things constant and look for these slopes. So keep the Reynolds number low to verify this law we believe in, right? 2 keep 2 of the quantities constant, vary a third, right? So as an example, drag. So let's say I vary the velocity and keep the, vary the velocity, keep the viscosity and the speed constants. I'm just varying the velocity, right? You do a bunch of experiments, which are these data points right here. And that's the C value you're looking for. That is the proportionality constant, or what ends up being is a coefficient of drag. You're looking for this thing experimentally. You could do it for the other things. I could keep the velocity and the viscosity constant and vary the diameter, and you get the same C value. So that's why we say it's a law. For the high Reynolds number experiments, those are the airflow ones. It's the same thing, right? You do this, you choose 2 to keep them constant, vary a third. Okay. And then for that situation, you need a different behavior, right, where it's now the drag. And now, since there are no square relationships, let's say I varied the distance squared, but I kept the other 2 constant. That means it's a linear relationship. Now, this best fit line, think of it as the coefficient of the turbulent part. So those are what those coefficients are. Just like the friction factors for internal flows, I'm sure you noticed that, right, this constant or coefficient of drag makes sense that it's a function of the Reynolds number of how this external flow is behaving, right? So it makes sense that we're gonna have, right, a coefficient of drag for laminar, because there was this situation here when we did these measurements. Let's say this is laminar. This is the turbulent part, right? So we're going to get a coefficient of drag in the laminar regime, which is this part, and then a coefficient of drag in the turbulent regime, which describes this part. So that little drop in transition is starting to make sense based on experiments. So these coefficients of drag, the proportionality of drag is proportional to these quantities that I square or multiply together. But what you really want is that coefficient value. What else do I have in here? Oh, yeah, the other thing is Reynolds involves diameter as well, but you could also you also tell yourself that these coefficients are also a function of geometry, right? So this geometry plays quite a big role in coefficients of drag, is the geometry in the flow. This number is really just telling you if you're laminar or turbulent, and it behaves. And we can get to actually the very, very, very reason these things go down. That's going to be later. But why would you want to calculate drag? Sounds like a silly question, but I like to ask myself these silly questions, right? Sounds like a silly question, right? But why does anyone care about drag, and why should we want to calculate it? Well, the picture you can draw in your head is if you have like an airplane that has to fly through the air, or just any body, right? So this is the velocity of the air, and it has to go at some velocity. Notice that if the velocity, right, if there's no gust of wind going forward, these are interchangeable things. So relative velocity is something you should keep in your head. So maybe I shouldn't have brought that up. But so this has to go at some velocity v. It's experiencing a drag force, right? It's experiencing a drag force it has to overcome. So, right, from physics 2, that power is equal to force times the velocity, right? So that's why you want to calculate this drag force, because then you can get a power value, because that would be drag force times velocity for the vector dot product, but right? And now you have a unit of power. This is now telling you, right, the power of the flight engine you would need to overcome all of these drag forces occurring based on the surfaces of the wings of the hull, of all the parts though. So you can kind of break it up, and usually that's what we'll do is you just look, well, what's all the drag forces happening on this surface, external flow? What about the external flows on this, like, let's say this is a cylinder, right? How about these things? Just kind of maybe calculate drags, and each of them, add them up, get a total drag force. And now you would know how powerful your flight engines need to be. That's the biggest reason you want to calculate drags, or at least motivates me to calculate it. But let's get a little more details and actually more of its drag coefficient.